Hello, everybody. Welcome back. In this lesson, we will go over derivative properties and graphing problems. The derivative has a variety of applications. Some of them are real-world applications, some of them are theoretical and yet useful applications. Now, uh, in this scenario, in this lesson, we will go over graphing problems, which can help us to see the behavior of a given graph. And what is the connection? The derivative tells you the entire description of the slope of the given function. And combining it with some other algebraic characteristics of the graph, you can pretty much visualize the entire form of the graph without any obstacle. So the derivative, in that sense, is a very strong property that we can employ in this exploration. All right, so to begin with, let's look at a few graphing properties, or few characteristics of graphs. Now, usually in applications, we will be given an expression. So that expression or the function in terms of variables that could appear from like a real world scenario. It could come with a statistical model. And when you have such a function, now when you try to look at the graphical behavior, or in other words, the shape of that expression, you need to employ certain characteristics. So what are these characteristics? Let me point out a few in this case. If you look at this graph carefully, on the very left side, you can see the graph is getting aligned with there's an asymptote, pretty much like it is getting aligned with the fixed value, right, at this point. So that kind of a behavior is called an end behavior. And of course, it occurs at negative infinity. Now, you can simply recall where this should belong, right? So when it comes to the the behavior of the function at negative infinity, you can think about that in terms of a limit at infinity, limit at negative infinity. On the other hand, if you consider the behavior right here at this point, it is associated with the horizontal, it is associated with the vertical asymptote. In the previous case, it was a horizontal asymptote. Now it is a vertical asymptote. So when you consider these two cases, if you can have two or three couple of guiding points in between, now you can roughly see this function even when that orange graph is absent in our picture. There could be some subtleties that we need to uh, consider carefully. However, there is a rough picture when you try to see just through the red guidelines of this function. The guidelines given in terms of red color, the behavior at uh, asymptotes, and then at these two local peaks and valleys. So these local peaks and valleys are really important in guiding our problems. So now if you look at similar behavior in the second component here, you can see a few local peaks and valleys for this function. And at the same time, if you accompany it with the behavior right here at the vertical asymptote and the behavior right here at the other vertical asymptote, we can have a good description of this function when we do not have the luxury of that orange function. And then the same thing is valid right here, in this case, right here, the asymptote. And then right here also, the horizontal asymptote, the function is getting aligned with that fixed height at that point. And then there is a local peak for the function. So now try to think about this. Now, in reality, what we are going to get when we have an expression is not exactly this orange sketch, the sketch of the function. It is not available. what we are going to get is what we are going to explore, or what we're going to explore and to analyze, in other words, would be just these red details that we put on this graph. So there could be critical points. Now, these kind of points, can everybody see? Can you see here? All of these points that we consider the peaks or the valleys, those are related to a special characteristic of the function, namely the derivative being zero. The slope is becoming zero at all of these points. Those are just horizontal line segments, horizontal tangent lines. So you can simply determine the locations of these red dots by looking at the derivative. And at the same time, if you can just look at the derivative and see like what happens here, right, in this region, if the derivative is positive, in other words, you're looking at a positive slope, in that case, the original function is increasing. So you can have all of these nice guiding points put together to get a very nice description of this function. So we will look at this more in detail in upcoming examples. Now, the first step, let's summarize exactly what kind of behavior that we can expect. Couple of things. Shape of the graph is guided by, of course, these red characteristics that we put, and we will have something slightly more, right? What are the characteristics that we can expect? We can have critical numbers, right? Critical numbers are exactly the points that we considered earlier, like those red dots. Not only critical numbers, once you have them, you can think about maximum value and minimum values. You can consider maximum and minimum only in local sense. If you look at what you see right here in this red circle, it is a maximum for the function locally. It is not gonna dominate all the other y coordinates. However, it can dominate all the y coordinates in a very small neighborhood. That's exactly what you see here. And then employing the derivative based on the positive or negativity, right? Positivity or negativity of the derivative, you can simply say increasing or decreasing intervals, because the slope positive would imply the graph is increasing. Slope negative would imply the graph is decreasing. Think about this scenario simply in terms of two straight lines with positive slope and negative slope. Which one is increasing, which one is decreasing? The same idea. And then both of these properties are coming from just the derivative. So I will just name it. These are coming from the first derivative. Why did I want to emphasize the first derivative? Because there will be a role of the second derivative in this conversation soon, and you will see that. And then apart from that, you can clearly see we can guide the graphs through the vertical and horizontal asymptotes, and vertical asymptotes are accompanied by or defined by undefined points on the domain. So not those are exactly the points where that are not included in the domain, and at the same time the function is having an infinite jump at those points. So these considerations are mostly given in terms of limits. We have seen infinite limits and we have seen limits at infinity. So can you see how small parts that we introduced separately are now being assembled together to get a holistic picture? Now, the next one is x and y intercept. Even in this case, I can just do these two together with the right. No, let's put these two, and then you can think about x and y intercepts. This is nothing other than algebra. How do you find the y-intercept? You know already, right? You're going to plug x equals 0 into that function. And to find x-intercepts, you're going to set that equation to 0 and you will solve it for variable values of x. That is algebra. You knew that even before getting to calculus. Now, apart from that, there is a nice story about the shape of the graph. To enhance the shape of the graph, you can think about the second derivative, and that describes particularly, let me just write it clearly here, the second derivative. Second derivative will tell you the story of concavity. And we will see most of these facts in this lesson itself. We will look at critical numbers. We will look at increasing, decreasing properties. Uh, we are not going to learn them just like theory. We are going to put it to the practical form, and we will work with that right away. And then when it comes to concavity, I will show you what it means and how the second derivative can help us to recognize it. All right, let's start our journey. The first derivative property. First of all, this is something that you do not need to take notes as far as you directly feed it to your brain. All you need to understand is the meaning of the first derivative. This is already known, right? The first derivative tells us the slope. So if it is the slope, if the slope is positive of a certain graph, then the original function f of x is none other than the original function. It is increasing. And if you reverse this, if the first derivative, or in other words, the slope, if it is negative, then the original function is decreasing. On the other hand, if you have f prime equals 0 at a given instance A, of course, this will not be expected to occur along an interval. Then it becomes a pretty boring example. We will see that later. But if you end up getting the derivative instantaneously equal to 0 at a given value A, at a given point A, how does that work? That simply implies the function is neither increasing nor decreasing at that point. It is just stationary for an instant, just an instant. Think about the dynamical process behind this. So the function can have a dynamic increase or decrease, and at a certain point it may get tired and it will have a short break, and that's exactly the situation where the derivative is 0. It doesn't increase or decrease. All right, so now if you recall this in the sense of the graphical illustration that we had at the right at the beginning, that's exactly the determination of those critical numbers. Critical numbers are exactly the local valleys and local peaks that you can see, right? So now, how can you find critical numbers of a given equation? It's pretty easy. We know how to compute the first derivative, and then we will set the derivative to 0. And once we do that, when we have the collection of solutions, those will place those red dots on the graph. Even if you do not have the graph right at the beginning, we are going to just locate them and then we try to navigate the graph. So critical numbers are going to play the most critical role in this analysis. That's a starting step. And then let's play with an example right away. All right. So I have some worked out write up already. And then I will supplement it as we proceed with this problem. Now, our problem is this. Sketch the graph of this function. Sketch the graph of f of x equals 2x cubed minus 3x squared minus 12x plus 11 plus 1. Now, what shall we do first? Now, first of all, look at this function. Can you see this was not in the catalog of our functions that we graphed already. We know how to plot a quadratic. However, we do not know up to this point how to plot a general cubic function. The degree of this function, this polynomial, is 3. So how can we do this? To do this, the first step, what I'm going to do first is none other than just to take the derivative. Let's take the derivative, the first derivative of this function. And you must be fluent with derivative computations at this point. Most of these examples that we have in our curriculum would not be too tedious in derivative computations. We have seen more complicated computations in our derivative computations. However, in real world scenario, you can expect any level of difficulty. Now, in this case, it's the most elementary. Just take the derivative. And once you do that, now you use the power rule and you take the derivative. And once you do that, in the next step, you need to simplify this. To which level? You need to simplify it to a level where you can see the solutions of that equation when you set it to 0. So when you do that, let me just erase this piece. It's not relevant. So now for critical numbers, this is what we are going to do. Once you have this simplified form of the derivative, we already simplified it to that form. So once we have that simplified form, now we are going to set this equation to 0. When you set it to 0, don't forget 6 is a positive value. So you can divide both sides by 6, leaving only this component equals 0. That will result to solutions. And in fact, when you recall simple algebra well, you can simply say from this point to that, you can jump to that. You can say, all right, so the solutions of this equation when you set it to 0 is going to be obviously x equals -1 coming from the first factor, right? And then x equals 2 coming from the second factor, and put them together, and that's what it is. And then let me show you where we are heading towards in the next step. Now, once we have this, the next step is this. We are going to organize this information on a grid or on a small table. Why do we employ tables? It is not essential, by the way. So organizing your information on a table is simply a way to summarize and way to convince yourself about like this scattered information. So I will employ pretty much this table for each and every problem. But when you work with it, when you earn experience, there is a way not to use this table and you can directly see the properties from your computations. However, now in this case, I'm going to use this first segment or the first line, first row, just to have the entire real number line summarized on this, right? What do we mean by that? Now, if you look at this very carefully, we need to have, now there is an increasing order for this critical numbers. So I'm going to do this. I'm going to have these two critical numbers in two places, -1 and 2. And I will have this left side right here open and in between open, and then the right side of the last critical number open. So now when you have two critical numbers, your graph or your table need to have how many columns? 1, 2, 3, 4, 5. Right? So there should be 5 columns altogether. When you have like, let's say 3 critical numbers, then you may need to add 2 more columns to indicate that too. So when you have any number of critical numbers, plan it ahead how many columns you may need. Now, what do I place right here? I'm going to say those are the x values less than -1. And what I'm going to have here, those are the x values in between -1 and 2. And then what do I have here? Obviously, we can see those are the x values greater than 2. Now, if you look at what we've written down here, in terms of these inequalities, we just summarize the entire real number line. Now, let's look at the next step. What is the value here? When x equals -1, we know the slope is going to be 0, and that's how we computed it. So f prime is going to be 0. And when x equals 2, f prime is going to be 0 again. And look at this too. Here we have the original function in the second column, and the third one is having, okay, the second row is talking about the original function. The third row is talking about the derivative of that function. So we cannot fill all of this information. Some of them will be missing no matter what. We will try to fill as much as possible so that it would guide the graph. How can we do that? Now, to do that, first of all, I will do this. Now, when x equals -1, what is the value of f of x? What is the y coordinate, in other words? This is the y value of the graph. So if I'm trying to place a point on the graph, I need to have x coordinate, I need to have y coordinate. So this will give us the y coordinate. To compute that, you need to bring this value and you need to go to the original function and plug it in. When you plug it in, what do you get? Plug -1 in the position of x. Wherever you see x, plug it in there and see what you end up getting. When you do the computation, you can see it turns out to be positive. Okay, so it's going to be -2 minus 3, and then positive 12 and plus 1. Now simplify this. If you simplify this, you can clearly see it turns out to be just 8. The same practice for the other case. If you plug in x equals 2 in this, what do you get? So do the computation in the original function. So it's going to be, now it's totally up to you. It is your computation, you do it. But let me do that for my information. I will get 2 and then 2 cubed, that's going to be 8, minus 3 times 2 square is going to be 4, and minus 2 times 12 is going to be 24, and then don't forget plus 1. Now we need to simplify this. We are going to get 16 here minus 12 minus 24 plus 1, and simplify it further. You will end up getting -36 here, and with positive 16, it's going to be -20, and then with plus 1, it's going to be -19. So minus 19 is the y coordinate. So this turns out to be -19. So that's only the computation of the y coordinate. Now, all of these computations are behind the curtain. You do not need to have all of these like minor computations. So I will just erase it. Be accurate, but apart from that, you do not need to include all of these pieces in your computations. And then all you need to recognize would be, now, there is no point of asking for all y values in between, like on these intervals. Can you see when x is between -1 and +2, how can you find the corresponding y values? If we know that description, we already know the form of the graph. So we cannot fill these 3 fields. However, when we look at this line, we can get some qualitative information regarding the derivative. Don't forget, the first derivative property says if the function is having positive derivative, the function is increasing. The original function is increasing. If the first derivative is negative, right? When the first derivative is negative, then that simply means the original function is decreasing. So all we need to have in these columns would be, those fields would be just a positive sign or a negative sign, plus or minus. we need to determine which sign the derivative has on each interval. To do that, it's really easy based on one amazing property that the derivative has. Around these critical numbers, in between two critical numbers, the derivative will not change its sign. It will always be uniformly positive or uniformly negative. Even though we have infinitely many values in this interval, x less than -1, all we need to do is to pick one value, like let's say x equals -2, and plug it in the derivative expression right here, and then from that you can determine whether it's positive or negative. Now pretend we use this expression, the form of that derivative, right? When you plug x equals -2, what do you get? Is it a positive value or a negative value? 6 times x plus 1 will turn out to be negative, and x minus 2 will turn out to be negative. So multiply two negatives and you will end up getting a positive. Similarly, pick a value in this interval. What is the most convenient value you can think of between -1 and 2? Yes, you can pick many other values. You can pick fractions. However, we can pick 0 also. 0 is very convenient in computations. Plug it right here in the expression in the position of x. You will get 6 times +1 times -2. So it's going to be negative. And then after this point, like let's say, again, let's have a candidate value for the third interval. Let's pick x equals 3. Let's plug it in the position of x in the derivative. And when you analyze each piece, you can see both of them are going to be positive and leaving this one positive. Now, this can tell us an amazing story regarding the shape of the graph. Look at this. Right before this point, now, if you look at the behavior at this point, when you pass through this critical number, this is how the function behaves. First of all, it has positive slopes. The function should be increasing. And then all of a sudden, at this point, it becomes stationary because the derivative is 0. It becomes just 0. And then it turns negative because right after that, the derivative or the slope is negative. And then similarly, if you analyze around x equals 2, this is how it would work. First of all, you have negative, and then all of a sudden at that value, the derivative becomes 0, and then it becomes positive again. So this simply means it's a maximum. We can call it a local max. It is locally, it's a maximum, and this behavior is a minimum. Can you see? A maximum locally, local peak, or a local valley. Right? Now, all we need to do is to bring this shape or bring this information to our graph. Here we have the x coordinate, and of course we have all the coordinates. Look at this, -1, +8. We know at -1 the y coordinate is +8. So this is one of the points. Let me put it in red. And then this point, the other point, we know those two. And then the shape of the graph on that right here would be something like this. That's exactly the shape. So I'm going to just import it to that. And then the second critical number is giving us this kind of upside. It's just a U shape pretty much, just like that. And then in between, we are going to smoothly connect the function. This is a smooth function, so we can just connect it like that. And then we can think about, like, now, let's think about what's going to happen after this point, beyond this point. It would be amazing if we could look for the x coordinates, or like x-intercepts. However, it's going to be very difficult. Solving equations is a very complicated scenario when you increase the order of the polynomial. So I'm not getting there. Instead, let's look at one important aspect of this function. Can you look at this function and say the behavior of this function when x goes to positive infinity and when x goes to negative infinity? Look at the original expression. Now, when x goes to positive infinity, all the terms are being dominated by one single term, that is 2x cubed. If you don't see this, think about some value, right? Let's say you're going to plug x equals 10. If you plug x equals 10, of course, 10 is way less than infinity, right? But think about just, I mean, relatively a small number, but yet a little bigger than 0, right? 10. When you consider 10, and if you plug it in, what do you get here? These values, this is going to be just 120. This is plus 1, of course, negligible. And this is going to be 300, of course. 10 square is going to be 100, and then with the negative it's going to be negative 300. However, when you plug 10, in this case it gets to the levels of thousands. So when you plug in large values in this description in the position of x, this leading term dominates all the other terms, and the behavior of this function at infinity is completely determined by the action of the leading term. Now with that, you can say when x goes to positive infinity, this term is heading nowhere except for positive infinity. It is skyrocketing all the way up to infinity. So let me draw that in my graph just like this. It goes all the way up. There is no control for that, and it goes all the way up. And similar to that, if you consider the behavior at negative infinity, right? If you consider negative infinity, yet you're including substantially large value in quantity. The value is large, but the sign is negative. Would it change the behavior? No, it's not going to change the behavior, because yet it is determined completely by this leading term. So what do we get when you plug negative infinity, or when you consider when the function goes to, when x goes to negative infinity, 2x cubed goes to negative infinity now, because it's a cube of a negative number, which turns out to be negative, and it goes down to negative infinity. Now, this is the rough sketch of the graph of this function. And you did not want to have much of information except for the first derivative. Now, you should really ask, uh, can we find the x-intercepts? Yes, technically speaking, yes, you can, but it's going to be extremely complicated in a random polynomial. So when it is not evident, we are not even giving an attempt. It's just algebra, but the calculus story is always better than the story behind algebra. And then when you consider the y-intercept, on the other hand, y-intercept can always be determined, because when it comes to the function, just plug x equals 0 in the position of x, you're going to get f of x, f of 0 equals 1. In other words, the y-intercept is 1. So that simply tells us one thing here. This intercept is none other than something that we know, it is just 1. Now, when we draw this kind of a graph, when we sketch a graph, we are not expecting the graph to be perfect. We are trying to see the rough behavior of the graph. So we can clearly see this is not up to a scale. The distance between 0, the origin, to 1 is not exactly uh, justifying the distance from 0 up to 8. So don't worry about scaling. We are not trying to perfect to see any perfection on our graphing. All right, so with that, let's proceed to the next half of this story. The next property is, now the next half is a second derivative property. What are we trying to do with the second derivative? The computation of the second derivative is pretty simple. How do we compute the second derivative? We differentiate the first derivative one more time. So in the previous example, in terms of the previous example, we look at the first derivative expression and we grab it, we differentiate it, and we will end up getting the second derivative. Now, when we have the second derivative, it has a story to tell. it will tell us the shape of the graph. In other words, the real meaning of the second derivative is how fast the slope is increasing. It is the slope of the original function. It is the derivative of the slope function. So if the slope is increasing, it will occupy this kind of a shape, a U shape, or a part of a U shape. It could be either this half of the story, just a part of a U shape, or the other half of the story, part of a U shape. By any chance, if the second derivative is negative, then it is going to be an upside down U shape. So it could be a part of that shape too, either the first half or the second half. Now, this shape, this U shape is what we call concave up. So we name this kind of a shape concave up. And that's okay. So we do have the technical term right here. Concave up is right here. Concave up. How can you connect it and not to mix it up with uh, these two scenarios? Because up, it corresponds to U shape. And then, of course, concave down is upside down U shape. So concave up is determined by the shape of U. And then the other one is evident. Now, concavity change. Now, the concavity can change at a given point. There could be certain points where it changes from a U shape to an upside down U shape. And we will see an example, just the same example that we saw earlier. Let's go back and analyze it in a moment. Until then, just have this in mind. Concavity can change. When it changes from concave up to concave down, or concave down to concave up. And the points at which it would occur are called points of inflection. To find points of inflection, this is what we do: simply take the second derivative and set it to 0. Just the same practice that we had in the first derivative. However, the catch is, in this scenario, it's not going to give you always points of inflection. It is going to give you a set of candidates for points of inflection. And not all candidates that you're going to get would pass through this concavity change property. Sometimes they will just pass concavity even without it making it subject to a change. That's the next level of examples, but let's try to stay in the context here. Now, a quick geometric exploration. What do we mean by concave up, really? We know it's a U shape, right? So let me draw this shape for now, concave up. I'm not going to do anything right here. We will see that in a moment, but concave up. Now look at this. This is a part of a U shape, right? It's just a part of a U shape. Now, can you see this has increasing slope? Of course, right? We can see it has increasing slope because the slope here is less, slope in between is little bigger, and slope later will be even larger. The slope is increasing. Now, try to see the other half. Now, I said like, I try to unify this, right? This and then this shape, the other part of the U shape. If I did not have it here, I could put it here, but other than putting it here, I broke it and I bring it here. And I'm trying to see whether that portion is occupying the same property of increasing slope. Can you see an increasing slope? Increasing should be when you move to the right. So when you move this way, the slope should be increasing. Now, this is a point where you may have some concerns. Look at this. The graph is more steep at the beginning. It's steep at the beginning, and then it becomes less steep gradually. So apparently it is not getting increasing slope, right? Now, this is where you need to think about not just qualitatively, but also in terms of numerically, in terms of the quantity, right? Look at this. If you consider the slope here right at the beginning, let's give a value. I'll call it negative 100. It is a negative slope, right? It's negative and yet it is steep. Therefore, I will give a large number to that. Now, if I need to assign a number here for the second slope, what do I get? What is the slope? Let's call it negative 50. It's yet negative, but it's now moderate. And then if you get to the third one, I would say like m equals even negative 10 or something. Now, if you look at the sequence of these values, what can you say? Is it increasing or is it decreasing? These values are giving you the slope. Is that sequence increasing or decreasing? In terms of the magnitude of numbers, yes, of course it's decreasing, but when you consider the negative sign, you can clearly see that collection is increasing. So simply either one of these components, or if you consider the entire combination of a U shape, right? So you can have one of these, either this or either that. It doesn't really matter if we drop that 0 over there, and let's have this shape together. Can you see all of these are telling us one simple story: slope increasing, or in other words, increasing slope, which means f double prime, it is associated with the second derivative being positive. So the same story, if you flip it to the other side of the fence, right? Now you will see this kind of a scenario. Can you see this particular situation? It's clearly decreasing slope. You have a large positive value at the beginning, and then this slope becomes less. And then when you consider this portion, the other part of the upside down U shape, you can yet see it is associated with the same idea. This is like negative 10, negative 50, negative 100. It is decreasing because it becomes more negative. So collectively, it's this shape. Oh, sorry. You should get red. All right. So this is concave down side of the story. This is concave upside of the story. And when it comes to concave down, we can see it is exactly the opposite behavior than this. So slope decreasing or decreasing slope is none other than it is if and only if f double prime being negative. I can indicate it by less than 0. So that is exactly the property that you need to understand behind it. Now the application. Now by any chance, if you have a struggle in understanding the nature of the second derivative yet, let's go back and summarize it. All you need to understand is, by definition, is this component, right? The second derivative positive, concave up, the second derivative negative, it's concave down, and the concavity changes at points of inflection. Now let's try to see this graphically. To see this graphically, what we are trying to do is to employ exactly the same function that we had in the previous example. Take the first derivative, here it is, and we simplified it to different form. In the previous case, we had a factored form, but do not get there. Differentiate it in this form because it's just a polynomial. You do not need to exhaust yourself by employing a product rule other than using a polynomial, just direct linearity properties. So when you take the derivative of this, it becomes negative 12x minus 6. Now at this point, if you set the second derivative to 0, that will give you potential candidates for inflection, points of inflection. And when you solve this equation, right? So you're going to get this equation 12x minus 6 equals 0. Now move x to the other side, so divide by 12. So 6 over 12, in other words, 1/2, positive 1/2. That's what you see here. Now, analysis of concavity, check concavity, simply means you do not need to look at the graph even. Just do this computation. Look at the x-axis, again, the same way that we broke it earlier in terms of the first derivative analysis. Look at it and have the potential inflection point listed on that, and then the left side of it and the right side of it. And there could be more than one single point coming out of this equation. And in that case, work accordingly to accommodate each number and their surroundings. And when you do that, what we are going to do in the next step is, now the second derivative, we know at 1/2, the second derivative becomes just 0. Let's use a different color because we are analyzing the second derivative. This is 0. And then let's check the behavior on the left side. So in other words, I'm going to get a candidate value in this interval, x less than 1/2. I will pick 0 simply. I will plug it in the position of x in the second derivative, and I will get a positive value. It's positive in that case. It's positive. And then let's pick another value from the other interval. So let's pick 1, because greater than 1/2, 1 would be a good candidate, simple enough for computations. Bring it here, put it in the position of x. So you will end up getting 12 times 1 minus 6. What is that number? That number is going to be positive 6 at the end. It's going to be, all right, in this case, it's going to be positive. Oh, I guess I made a mistake in my previous computation. Is this correct? Do you buy this? Is this positive actually? I guess it's not, right? When you plug x equals 0 here, you end up getting just the first part becomes absent and the second part becomes negative. Oh, let me just do that correction with the red pen. All right. So we have negative to positive. Now, if the second derivative is negative, what kind of shape the original function should have? It should be upside down U shape. And then what kind of shape do we have in, I mean, we should have in this scenario in the right interval, it should be this kind of a shape. This does not mean it need to be the entire shape. It could be a part of it. It could be like this, it could be like that, but like this or like that in that scenario. Any part is possible. And then in between, can you see at this point, it changes when you pass through this point, it changes from concave down to concave up. Now, does this add up? Let's try to see it in the context of our previous example because we already did that, right? Let's go back. And since we have this amazing graph already, why don't we copy it and bring it to our current problem? And I'll put it right here. Let's do this. Oh, let's do it carefully by bringing it in right here. Look at this very carefully. This point 1/2 here, if you try to put it in this problem, it appears somewhere between 0 and uh, 0 and 2, right? So 2 is right here. So it should appear somewhere in this region. And that value, when we plug that value, let's say 1/2, and that will correspond to a value on the graph. You can find the corresponding y coordinate if you like. That will be just bringing it to bringing x equals 1 half to the original function just to find like what kind of height you have here. But now what we need to understand is the shape of the graph where it changes from concave down, upside down U shape from here to a U shape in this. So concave down to up. That change occurs right here at this point, the point of inflection. So that is a graphical meaning behind concavity. So even without knowing or even without looking at the behavior of concavity, we were able to plot this graph. But now can you see when you have the information about the second derivative, your knowledge or the shape, the way that the graph would look would be enhanced. You can enhance it substantially. You can see where this change of concavity, concave up to concave down, in this scenario, concave down to concave up, upside down U shape to the U shape. It is a very smooth transition occurring at this point, but you can recognize that particular point. All right, so with that, let's proceed to another example. Now, being the first example, I try to provide the background, the computational background. Now, starting from this point, I will try to make it like just computational. Sketch the graph of this rational function. Now, I told you, you can plot pretty much any function. It need not to be a polynomial. It could be even including trigonometric, exponential, logarithmic functions. That is the amazing part about the derivative. So once you consider the derivative here, the first thing, compute the derivative. And here, I'm not going to explain exactly how the derivative computations are performed. You should be able to do it, right? You know how to take the derivative. It is none other than the quotient rule. And when you take the quotient rule, first of all, this is the first level of application. And then we do not leave it right there. We simplify it further. Now, my recommendation, since you know this story, pause the video, have these steps like guidelines, and try to connect the dots in between these computations. It is your duty, and pause the video and do it. I hope you gave it a try, and I hope you understood exactly the process of the computation. Now, given that you safely got to this point, now set that to 0. If you set this equation equals 0, if you equate that to 0, after the cross multiplication by this term in the denominator, you will end up getting just the numerator being 0. And then when you divide both sides by this positive number 4, you will end up getting only this piece. These two linear factors equal 0. That simply means once you get to that point, uh, here, once you get to that point, you can see the the critical numbers. The critical numbers are donated just by these two factors, and all the other pieces are just distractions in the computation. So when you set those two factors, you will end up getting x equals -1 and x equals +1, and then I will write them in increasing order, because in the next step I'm about to organize them on my table. Now let's do that. Now when you try to have it in the table, the first step, at -1, what is the corresponding function value? Now this is the original function, this is the derivative, right? Do not mix up those two scenarios. So when x equals -1, now I'm going back to the original function, plug it there, and get the corresponding value. What do you get? Yes, it is -2. And then when x equals +1, take it there and plug it x equals 1. What do you get for f of x? That would be just +2. And then in the meantime, we know at these two critical numbers, we found the critical numbers in a way that the derivative becomes 0 at those points, right? So we do have that. And then what we're trying to do is to check these three pieces qualitatively, see what kind of behavior we have for those three places. Either it's going to be a plus or a minus. Is the derivative positive or is the derivative negative? To do that, we will pick candidates values of each interval. X equals -2, x equals 0, and x equals +2. Bring them over to the expression of the derivative. First of all, starting from -2, right? Bring it and plug it in the position of x everywhere. Now, when you do that, there are a couple of things. Now, when you're familiar with computations and the forms of functions, some of the computations can be eliminated. You do not need to plug this value and you do not need to simplify everything. Look at this. The term in the denominator is a square, a complete square. No matter what, it's going to be non-negative. So it's not getting involved with this computation. It's always positive. Factor 4 is always positive because it's a positive number. All you need to do is to analyze these two pieces when you plug in those values. So plug -2. In this position, you're going to get -1. And when you plug -2 in the position of x here, don't forget there's a negative sign inbuilt in front. So that would make it positive. So positive and negative will make it a negative. And then when you consider 0, when you plug in 0 right here in the position of x, you can see it is clearly going to be a positive value. It's going to be just positive. And then when you plug x equals 2 in this place, you can see the first factor becomes positive, the second factor being negative. So it's going to be again negative. Now, let's try to plot this graph roughly. X coordinate and the y coordinate given here. So x is -1, y is -2. So I'm going to put that value here. Let's employ blue. And right here, it's 2 is going to correspond to the y coordinate when x equals 1. Now these are 2 points. Now can we see this is like negative slope to positive slope. So it's a mean. So this shape should be a minimum. And here around this critical number, what you're going to get is a positive to negative. So it's a max. So it looks like this. Now the other background information would be when x equals 0, you can find the corresponding y-intercept right here. So the function should smoothly connect from this point to there like that. And then the question is, what's happening in the left side and the right side? What is happening? What's going on there? How can I complete this half of the function? Should it be like this, or should it be like this, or should it be like that? How can you make sure? To see that, you can explore more properties. Now, clearly one can see it cannot be something like this. If it turns back, that means there is another critical point here. But how many critical points did we get for this function? We had only two critical numbers, right here and right there. So that simply means, since we have only two local extremas, based on two critical numbers, there are no more critical numbers. So it should be either like this or like this. But then when you think about the scenario, you can answer it in many ways. Now, one thing that you can do is to look at the end behavior. You can see like, oh, let's question what's happening in the right end. When you try to do that, limit x goes to positive infinity, 2x, or like let's say 4x, it should be the function divided by x squared plus 1. You can do a minor computation, minor limit computation. Don't forget this is a limit at positive infinity. We know how to compute it. When x goes to positive infinity, you will end up getting the computation is performed by dividing every term by x square, which is the largest term of x in the denominator. So when you do that, we can see the top and the bottom has fractions and both of them are heading towards zero, leaving only one non-trivial non-zero value in the denominator. So it's going to be 0 divided by 1 plus 0, leaving 0. So when you consider the right limit, right end limit, it's going to look like this. It should look like this. It's aligning with that. Now one can argue like, okay, why does it go like that? You can approach y equals 0 in this way too. But if this is the case, the function should go through and catch, and that will introduce another critical number, which is not a possibility. So having this kind of a behavior is impossible. Instead, it's just a smooth continuation towards infinity, continuation towards 0 when x goes to infinity. The same way, if you replace this infinity by negative infinity, you will have exactly the same value. The value will be exactly the same. That means in this half, it should be extended to 0, aligning with just 0 in the left hand. So that is the form of this function. Now in this scenario, you did not want to employ the second derivative in your computation. However, if you try to do the second derivative computation, it can enhance your knowledge about this, the behavior of this function. How can you proceed? What can you do? Now, in this scenario, this is what I'm going to do. Let's say, can you see, can you guess? There is a U shape somewhere starting from here all the way up to somewhere here. A U shape. And then after a certain point somewhere here, in fact, let me just make it look better. If you consider somewhere, a point somewhere here, there is another U shape right there, but it cannot be seen like a U shape because it's extended too far. It is an extended U shape. On the other hand, when you consider these two components, you can see right here, it's an upside down U shape, and here it's upside down U shape too. Extended upside down here, and apparently visible upside down U shape right there. So you can see concavity directly in a certain way now, but if you try to answer like, okay, what are these locations? Can you say something more about these locations? If you would like to explore that information, the only way is to look at the second derivative. Now, in this problem, it is not demanding us to do anything regarding the second derivative, but I'm going to do it anyways because it's about practicing. Let me go back to this expression of the derivative right here. And I will grab that expression. I will take the second derivative. So what I'm going to do is now f double prime x is none other than one time derivative of this expression, right? So let me just copy and paste it right here so that I'm not gonna miss information when I just try to do the computation. Now let's do the computation. Now when you do the computation, we can see it's again the quotient rule. So just, you know what to do. I'm going to do the computation without saying a word. Just follow. Or do the computation first and then check my work to verify your work. In that way, you will earn more confidence on your computational ability. All right. All right. When you work with mathematics problems, usually it is good to do it in a quiet environment, so you're not going to get unexpected mistakes. So here, that's what I try to do. And now look at this. Here I have 8x. Think about how I got it. I just differentiated the top and I got negative 8x. Is it accurate? Check. And then I'm going to do the simplification in a way where I'm going to have all possible uh, common factors of the numerator. But in the meantime, I need to fix something really quickly with the denominator, because now you need to square the denominator, and I did not square the denominator. I put it just as it is. So when you square the denominator, it turns out to be the square of the given term. It should be just like that. And now let's simplify. So the numerator will give you negative 8x and then one copy of this. Can you see there's one copy of x squared plus 1 available? And how do you get negative 8x out of the rest? You can simply say this one and this, right? You combine them and then it becomes positive 8x, and with this negative sign you can make it negative. And then when you take negative x times one copy of x squared plus 1, what you're going to have in the first term is just x squared plus 1. And then minus, since you gathered these two pieces, 4 and 2x, you gathered both of them. Here I am going to get only one copy here together with 2. That's all left. Even this negative sign is out now with the factorization right here. So what I'm going to get is 2 times x squared 2 times 1 minus x squared. The whole thing is divided by 4 copies of x squared plus 1. Now simplify. 1 copy of x squared plus 1 is right here. 4 copies are available right here. I will get rid of one of them right away, leaving just 3 copies in the denominator. And then negative 8x. And then simplify this term. Distribute this first. And then simplify and do it. Take a moment to do it. And then you will end up getting 3 minus square of x as the final simplification. Now, if you simplify this further, you can see you can have a factorization. Of course, this is a difference between two cubes. So square root of 3 minus x, let's utilize just parentheses, then brackets, root 3 plus x. The whole thing is divided by x cubed plus 1, sorry, x squared plus 1 to the cubed. Now, that is the ground level that we can see for the second derivative. This is our second derivative computation. Now, at this point, if you set this to 0, you can see all the zeros are coming from the top, as we mentioned earlier, from the numerator. And those zeros are going to be x equals negative root 3 And then from this component, you're going to get 0 and positive root 3. These are the possible points or values of x for points of inflection. And what is the role of these three in our graph? Now let's remember, when you consider root 3, square root of 3 is approximately 1.732 something. All right, so 1.7 approximately. That is what we are looking at. Like the ballpark should be just around that value, right? Now let's go ahead and check our graph. 1 is here, and then this is a location where we had the change of concavity. Can you guess that value? That is exactly root 3. And then this is the other value where we had a change of concavity, concave down to concave up. So it's down here, and concave up here, and concave up there. So that concavity change occurred, one at right here, the other one is right here where the x coordinate is negative root 3, and right here the third value where you can see concave up to concave down, that is exactly 0. So that is the third point of inflection in this consideration. So when you do this computation consistently, you can clearly see how these things are adding up. That is the amazing thing about the consistency in mathematics. All right, so with that, in this example, I can guarantee now, by any chance, if you felt this computation is like a little overwhelming, it's totally understandable. Don't get discouraged. Do this computation once more from your end. It could be a struggle right at the beginning. Try to do it. I wanted to show you a little bit of a tedious computation so that you can see how actually things would work out. And yet, it gives you a perfect picture at the end. All right, let's proceed to the next part of our exploration. Let's sketch the graph of uh, g of x, which is given by x e to the negative x. Now in this scenario, I did the computation ahead of time. My recommendation, just pause the video and try to see whether you end up getting consistent computations. If you do not see a consistency in this computation with your answer, that's exactly when you need to go ahead and check the rules of differentiation and brush them up. And here in this case, after finding the derivative and after the simplification, when we set it equal to 0, don't forget the exponentials are always non-negative, so only the polynomial components will donate the critical numbers. In this case, namely, it is going to be just x equals 1. And once you have it, now you can do the first derivative analysis. Now here I'm trying to put both of these tables together and show you, like, sometimes you can just simplify things just right away. And then when it comes to the second derivative computation, we can see the second derivative is the derivative of the first derivative. So grab this function and then take the derivative one more time. That's exactly what I did here. And of course, it's a product rule. And by using the product rule and the simplification, after the simplification, it will land on this scenario, right? Now, once you do that, in the next step, what you're trying to achieve is exactly uh, this first derivative and the second derivative analysis directly, right? So when x equals 1, first of all, I'll do I'll look at the original function. Don't forget the original function. I need to have the corresponding y coordinate. So when I plug x equals 1, I would get e to the negative 1. In other words, it's 1 over e. Whatever that value, it is just a constant, right? 1 over e. And then we know at this point the derivative is going to be 0. And on the left side, when you consider like a value, let's say 0, you can plug in 0 here. Okay, the 0, uh, which is not going to give us uh, much for the derivative unless you look at the correct version of it. When you plug x equals 0 in this expression, here you can see the first component becomes 1 and the second component is 1, 2. So 1 times 1, it's going to be positive. And then let's plug x equals 2, a value from this interval, a candidate. Let's plug it. You can see this component being negative in that occasion, leaving the entire term negative. So you can clearly see the function, the graph looks like this at that critical value. So it should be a max. And then at the same time, I'm trying to see what's happening with the second derivative. I'm being lazy here by putting both of them together to get done all the uh, work in one single location. So when I consider x equals 2, the second derivative, of course, by computation, we know it's going to be 0. And then when you plug in a value, right, from the left interval, let's plug in 1. When you plug it here, you can see the second derivative is negative, and then plug in a value here. Let's say x equals 3. When you plug it in, you can see this becomes positive. The first one becomes positive. It's positive. So it's going to be concave down in this scenario. It's an upside down U shape, part of it, or a stretch version. It could be anything. And this is concave up. So concave up. Okay, in here it's down and here it's up. Let me be more clear with that. So concave, if you try to analyze your concavity in the same picture, it's going to be just like that. Concave down here and then concave up there in the last interval. So that's exactly what we are thinking about. Now let's try to plot this scenario, plot all of this information in one figure. When x equals 1, 1 over e, it is just a value, non-negative value, a positive value. And then you can see when x equals 0, it goes through 0. Look at the original function, look at the x-intercept, look at the y-intercept, and that's what you have. And then you know it's concave down throughout in the interval from 2 to, right? So the next point that you need to consider is 2. 2 is a critical, it is actually a point of inflection. So I will mark it in a different color. So now let's try to put them together. Here you have a maximum, just this. And then it goes through 0. And then it goes all the way down to infinity because it remains forever concave down. It remains concave down, therefore it goes just like that. And then on this half, it turns and it goes through this point. I'll mark it again. This is the potential point of inflection. And then it goes like this. In this scenario, the reason is now when you look at this component right here, starting from this yellow point to the right, you can see a stretched U shape. It's a very long stretch U shape, therefore you cannot see it's actually a U shape, but it's concave up on that case. And then when you consider what's to the left in this, it's just upside down U shape that's concave down. And the parts that I would like to ponder, right, think about is why it's actually aligning with infinity, why it's aligning with zero when x goes to infinity. Why shouldn't it go like this? If it happens, now think about the concavity picture in this. If it's concave, if it is about concavity, is it gonna match with this scenario, or should it with match with more like this kind of a scenario? Because the slope should be increasing. If the slope is increasing, it becomes like less negative. Okay, so it becomes less negative in uh, the values of the slope. So that is how you can argue in that kind of a scenario. So that is the graph of this kind of a function. Now, the interesting aspect of this example, look at this. Here we are dealing with functions coming from two different universes, a polynomial component combined with an exponential. Yet, calculus has the amazing ability to visualize all of these pieces as far as you have a little bit of computation on your hand. As the last example, I will just open up this example. I'm not planning to work with it, and I'm gonna give you just a starting couple of steps. Now, in this scenario, the interesting part about this function is having undefined points in the denominator. In other words, you will have horizontal, in other words, you will have vertical asymptotes when you have undefined points. So now I'm giving you this background information just for you to work with. And I'm not in, it's not my intention to work with this example by filling out all of this missing information. But now you can see how it is happening, and then pause the video, work it out and see, check whether you can tally exactly this work. And then in this scenario, I am not explaining anything with these two pieces. Why I am not putting anything in the uh, position of even the derivative in these two situations. Think about what would happen at -1 and +1 in this function. What are the undefined points? X equals -1 and x equals +1. So when the function is undefined, there is no way that you can define a derivative, so the derivative has no meaning. And then when you proceed, I will give you the shape of the graph. What you need to do is to match it with your consistent work at the end. So the shape of the graph is going to be like this. First of all, it's having an increasing derivative, and it has a horizontal asymptote and a vertical asymptote. So it would look just like this. And I encourage you to ask why. Reason from the beginning to the end. And then when you look at the last interval after, okay, so this is from -1 to +1. So when you consider the last interval after 1, what do we have? Beyond 1, it's going to be just negative. The derivative is going to be negative, so it's consistently decreasing. So it would look like exactly symmetric with what you saw in the other case, just like this. And what you're going to see in between is the behavior around this critical point, right? So this critical point, what you see around this critical point is exactly, it's going to be a maximum. with x coordinate being 0 and the corresponding y coordinate being 0. So I'm just trying to get that information, align it with the vertical asymptotes and say, this is how it would look. Now you need to understand the background story, the background of this by computing each and every component. So my recommendation, go back in the computational step, pause it right here. Do all the computation from the beginning to the end so that you can convince yourself. And in this particular problem, I'm not encouraging you to work with the second derivative. So it is just the first derivative analysis to see the basic graphical representation of the function. And then based on this table, right, starting from this table, can you visualize this graph? You need to work with this example as much as needed to see the connection. That is why I did not provide all background information in this, but I provided the framework as much, just say sufficiently enough. I mean, sufficient enough for your understanding, and it's your duty to connect the dots. All right, so with that, we will conclude this lesson regarding graphing functions utilizing first derivative and second derivative properties. It is amazing how much the derivative analysis can do. It doesn't really matter what kind of function you're looking at. As far as you know how to differentiate, you can talk about the variation of the function, the way that it increases and the way that it decreases. And based on that, you can analyze a whole lot. And that's exactly what we have seen here. We utilize the derivative properties, namely the first derivative to recognize the maxima and minima, including increasing and decreasing portions of the function. And at the same time, we can utilize the second derivative to see how the graph would look like, whether it's a U shape or an upside down U shape in a given portion, because that can enhance the way the graph would look in your drawing. So I highly encourage you to have a summary of this, because this is exactly the point of all the applications of calculus begin. So once you understand the graphical meaning, you can convert it into a variety of applications in different domains. So we will meet with our next lesson, right? In our next lesson with further applications, some are oriented towards real world scenarios. Until then, enjoy problem solving in this amazing section of applications. Have a wonderful time.